Peak Human.
Les humains à leur meilleur.
C'est tu apogeo.
ピーク人間
Pitówka niewiód.
Hello, everyone. Welcome back to the Peak Human podcast. I'm Brian Sanders, and I'm Food Lies on all social media outlets, so check me out there if you haven't yet. Today, I have a great one with Dr. Jason Fung, whose work I've been following for many years. He's really great. He wrote a few books, The Diabetes Code, The Obesity Code, and now The Cancer Code. He is on point with his stuff. I've always loved his work. He's really into the nuances like satiety and hormone signaling and how food matters and what you eat dictates how much you eat and why we don't need to count calories and not eating all the time and intermittent fasting. So many great things. And now he's come out with this awesome book, The Cancer Code, which I just finished right before I interviewed him. And it's a whole new way to think about cancer. It's super interesting. I love it because I really like unifying theories that bring concepts together. And I think you're going to love this one. So check it out. Listen to the end. Dr. Jason Fung is a Canadian nephrologist. He graduated from the University of Toronto and completed his residency at the University of California, Los Angeles, my alma mater. He lives and works in Toronto. He's a world-leading expert on intermittent fasting and low carb, especially for treating people with type 2 diabetes. He has written 3 best-selling health books, and he co-founded the Intensive Dietary Management program. And now, what's going on with me? Well, I had a great Thanksgiving traveling with friends. Guess what? You can travel. The government can't tell you what to do, and there's no restrictions. You just get on the plane and go. It's fine. I hope everyone had a good Thanksgiving and visited their family and used precautions if necessary, but otherwise didn't let government officials who don't have your best interests in mind dictate what you do for Thanksgiving. Now on to my usual disclosure that I take no outside money from any companies, and this podcast and everything I do is all supported by the community or powered by products that I make and care about. Now that's just 2 things. It's nosetotale.org and sapien.org. This is all I have to support my team and to support this show and all the work I do. All of them are great products. We're making new ones by the day, by the week. The body care products are selling out like crazy. We keep trying to make more. It's all handmade, so it's a little slow shipping right now. But please get those. I'm telling you, best body care products I've ever used. Only body care products I use now, other than some Redmond toothpaste that's really natural. They don't give me any money, but I will support Redmond because they send me some free salt and toothpaste every once in a while. We're also making the South African biltong products and Drovors, which is the meat stick version, and the biltong is the jerky-like product that's way better with the high fat, very tender, better than any jerky ever made, and better than any biltong made. You can listen to how it's made on the podcast I did with my business partner from South Africa on this, who has all the special techniques to make it the best that you can buy in America. So get that at nosetotale.org. We also have all the meat there that you can get in a box shipped to your door in the 48 states. A great thing about it is most people, and like myself, don't eat a lot of chicken and pork because it's not raised well and it has a lot of omega-6 compared to omega-3. But we have the high omega-3, low omega-6 version. We have a special diet and it makes their fat and their meat a much more ancestral ratio. So get that on nosetotale.org along with the primal ground beef that has the liver, heart, kidney, and spleen mixed into the ground beef. All grass-fed, grass-finished, well-raised stuff. So get that at nosetotale.org. And then sapien.org, we have our program. So if you are looking to lose some weight and make some lifestyle changes, we have your back. We have a program especially made for you. It's half off right now. We have health coaches, we have videos, written content, diagrams, all the things to help you implement in your life. Because, yeah, that information is probably out there for free. You could probably listen to all these episodes. It just might take you 200 hours. But the hard part is implementing it, figuring it out, personalizing it to yourself. So just go to sapien.org and you can scroll down and find the program there. We also have the tribe. If you want to get the bonus episodes of these podcasts, the extended show notes, the private members area, the Zoom calls with myself and Dr. Gary, and some other stuff like some discounts to nosetotale.org. So that's about it. Let's get on to the show with Dr. Jason Fung. Let's think about cancer in a whole new way and realize you have more control than you think. Please enjoy it. All right, we're here with Dr. Jason Fung. Finally got him on the podcast. Really excited about this. How are you doing today?
I'm good. How are you, Brian?
I am fantastic. I just finished your new book, Cancer Code, and I love all your books. You've read books on the three biggest topics, right? We have obesity code, diabetes code, and cancer code. These are the three biggest things that are affecting our society.
You know, it's just they're all related in a sense because we're all talking about sort of chronic diseases these days. I mean, obviously, there's different things that affect us like COVID and stuff, but the issue is that a lot of these infectious diseases and stuff that used to really kill people sort of year after year after year, they aren't the biggest killers. I mean, right now, of course, we're in a global pandemic, but most years you're talking about cardiovascular disease and cancer running sort of 1 and 2. And stuff that's creeping up is like Alzheimer's disease and diabetes and stuff. Like we're not talking about sort of malaria and TB and stuff that used to kill a lot of Americans sort of 100 years ago. So it's a whole new world in a sense that we really need to focus on these sort of lifestyle conditions where we can make things better. Not with medications, because medications is sort of last century, you know, where the idea is you come in and you get an antibiotic or an antiviral or whatever, and then things will be fine. Like things won't be fine. Like you take a pill, it's not going to be fine. You still need to deal with the underlying condition of type 2 diabetes or obesity or whatever it is. That's what these are, and I hope that people read them with a sort of fresh view and say, well, this is a different way to think about it, and at least maybe come up with a deeper understanding of what they can do themselves to potentially help themselves.
I love that. We can't look at just the symptoms. We need to look at the root cause. And what you're kind of saying over your career is there is this consistent root cause, and it all revolves around hyperinsulinemia and just problems with blood glucose and your body's response to that. And it's not some crazy mystery. I think a lot of stuff we thought was some crazy mystery, especially cancer. And I just finished your book, and now it seems a lot more not mysterious, right? You have some new ideas that really make things come together. And even with COVID, we thought it was this crazy mystery. Like, why are some people dying and why are some people aren't? Well, now we kind of know it's the metabolic damage that people have done, and more people are older, have more metabolic damage. And it's not so much a mystery. So
yeah. I mean, it's definitely true. The more we can understand about a condition, the better off we're going to be. And cancer is really this real mystery. It's been a real mystery for years because it's this sort of strange disease. And it's really unlike any other disease that we look at because it's sort of develops from our own cells. That is, it's sort of our own cells gone rogue and now killing us, which is different than anything else we face. It's not like heart disease, which is a blockage in an artery, or a stroke, which is the same sort of thing, but in the brain, or type 2 diabetes, which is a metabolic disease, obesity, which is a dietary disease. These are all different, but cancer is not any of those things. Like they contribute, but it's not purely a dietary disease. It's not purely a toxic disease, and it's not purely a genetic disease. It's something very different. And I think that what's interesting to me is that for all its difference, people don't really talk about what cancer is. Like we talk a lot about treatments of cancer, what drugs you need, what surgery you need, what radiation you need, and all that kind of thing. And those are important questions. But from an intellectual standpoint of what is cancer, not a lot of people talking about that. And that's why I found the whole discussion very interesting the more I got into it, as to what actually are we talking about? What is this disease, right? So, and that's where, as you take a look at the sort of evolutionary paradigm of cancer, which is what we've moved to rather than this purely genetic sort of thing. And the reason evolution is important is because it involves the genetics, but it's not just the genetics. It's the interaction of the genetics and the environment that sort of shapes how these things evolve. So you have to look at both, because for years we just looked at the genetics of the problem and got nowhere, honestly. It was, 25 years of very little progress in cancer therapeutics. And the sooner we face that, the sooner we can move on to the sort of next understanding, which is let's take into account the ecology, the evolution of how cancers develop, and what cancer is. Because again, cancer is not a single disease. It's all these, you've got lung cancer, which is due to smoking, which has nothing to do with, say, breast cancer because the lung and the breast are separate tissues. And smoking, while it does increase your risk maybe a little bit for breast cancer, not a lot. It's not like smoking, the way it affects lung cancer. Nobody had ever talked about, we never thought about that as a single disease before. Like, what are the commonalities? And that's really where things get very, very interesting because, something that people have started to talk about only in the last sort of 10, 20 years. Prior to that, everybody just looked at it as separate little silos, right? So prostate cancer is this, and colon cancer is this, and this is this, and this is that. But they're all cancer.
I love that. And we're finding out how beneficial that is in all of healthcare to not just look at one part of the body. You can be a doctor of the entire body, and the best doctors are the ones that look at the body as a whole. I love also that in the book, you do go through the history, and we have had we're in the third stage of how we understand cancer. So maybe you can go back a little bit and just tell people, what is cancer and how does it form and what did we think of it?
Yeah, sort of what happened is that the way we think about cancer really dictates how you treat cancer. So that's why these paradigms of cancer are really so important. So the first paradigm, which was sort of the modern paradigm, was that cancer is really a cell that grows too much. So the logical solution then is to kill them. So if you want to kill cells, you can cut them out like surgery, you can burn them like radiation, or you can poison them like chemotherapy. And that's not to minimize the contribution of those treatments. I mean, it was a huge advance. I mean, all these drugs, yes, they're toxic because they're ways of killing cells, but at the same time, they still form the basis of our treatment of cancer today. So it's not to minimize them, but that is what they do. Let's just face it. It's a way to kill a cell. And if you're lucky, you kill the cancer cell slightly before you kill the patient. That's really the whole basis of that paradigm of medicine. By the 70s, as we started to understand more about genetics, we started to say, well, we know cancer is a cell that grows, but why is it growing so much? And as we understood about growth genes, for example, we said, well, cells have genes that control growth. And if you have a random mutation in a gene that controls the cell growth, you can get a cell that grows too much. And we said, hey, that makes perfect sense. So you have these things that we know cause cancer, like smoking, and they cause damage to the DNA, which causes you to repair it, which causes mutations when you're trying to repair it. Hey, that makes perfect sense. Viruses can cause gene mutations and all this sort of stuff. So it made perfect sense to say, okay, what you've got is this genetic mutation, which is relatively random. That is, smoking, for example, is not a targeted genetic manipulation the way that we do with CRISPR or some of these other very high-tech things. It basically is just a random thing. And again, this was a huge paradigm shift because now we're shifting from cells that grow too much to genes that cause cells to grow too much. And the reason that's important, again, is because it changes your treatment. So now instead of trying to develop drugs that just kill cells, what you try to do is develop drugs that fix the genetic problem. And the first few drugs that came out were amazing. They're totally transformative. It was through the 90s we started getting these drugs such as imatinib and trastuzumab, which really transformed oncology and led to this whole optimism that we would cure cancer because there's this idea that you could do personalized medicine. That is, you could find out the genetic problem of this cancer and then look on your sort of, I'll use this drug because this guy has this mutation. And so we thought we were on the verge of curing cancer by the 2000s. All we were going to do is look for a couple of genetic mutations for breast cancer, identify them, find a couple of drugs that work, and boom, and do the same thing for liver cancer and do the same thing for colon cancer. So then we got the Human Genome Project, which sequenced the genes of one entire human being, and we were no closer. And then we did the Cancer Genome Atlas, which was instead of sequencing one human, we sequenced 33,000 tumors. So you take, say, 1,000 breast cancer samples and you say, let's compare them and see what genetic mutations are the most common. And of course, things didn't work out the way we thought they would. We thought we'd find 1 or 2 mutations for each cancer. Turns out each cancer had probably something like 50 or 100 genetic mutations. So that, of course, makes it impossible to treat because you can't give 100 different drugs for one patient. We don't have 100 drugs. We have like 5, right? So the problem is, of course, that it was all different too. So if you have 2 patients in an oncology clinic, patient A with colon cancer, you need 100 different drugs. The person sitting right next to that other one, patient B, would have 100 mutations, but 100 completely different mutations from patient A. So it's like, okay, now you're really screwed because you need 100 completely different drugs for this patient B in the next chair. And it's like, that's impossible. When they map out like all the mutations we found in cancer, it's around 6 million different mutations. It's like, okay, there's a ton of mutations here, and all different mutations from one person to the next person, even with the same cancer type. And even within the same person, you'd have different mutations within the same tumor and different mutations within the metastases and stuff. So completely unusable paradigm of medicine. And that was the big reason why this personalized sort of therapy, it just didn't deliver. It was impossible. It turned out that that paradigm could go nowhere. And so that's sort of where we were by the 2010s. We really hadn't made a lot of progress. And what happened, of course, is that if you look at the top killers of Americans, it was heart disease and cancer. In about 1960, heart disease was about twice as likely to kill you. By 2020, it's about equally likely. So clearly we had been making a lot more progress in heart disease than we were in cancer. It was like slow going. So that's sort of third big paradigm of cancer. That is what causes it. So again, it doesn't invalidate the previous paradigms, but it basically tries to go one step above. We know there are genes that make the cell grow too much, but what is controlling those gene mutations? Because it's not random. The whole idea was that this was actually an evolutionary process, because only one sort of force in the biological universe can kind of coalesce all these different mutations into a workable phenotype, right? And it turned out that the surprising answer was that these cells were mutating but not sort of mutating into a more developed form. It was mutating into a more primitive form. So it was sort of a backwards mutation. That is, the cells were actually not trying to become more developed. They're trying to be more like unicellular organisms. They were mutating backwards. That is, all these more recently evolved genes were the ones who are sort of being mutated. They're being taken off to sort of release this sort of inner sort of survivalist cell. So basically, in a multi-celled organism, the cells become specialized to benefit the whole. So if you have a lung cell, it doesn't exist for itself. It exists for the good of the whole sort of organism, which is us. And a lung cell becomes very specialized. When you subject it to chronic damage like tobacco smoke, then what can happen is that it may sustain damage, but it has a choice at that point. Either it will die or it can try to become sort of this survivalist. It can get rid of some of those more specialized programming and try to revert to being a more survivalist programming, which is like a single-celled organism. And the problem with that, of course, is that now that lung cell, which is now in the process of transforming into a cancer cell, is only concerned about itself, right? It's only concerned about its own survival, its own growth, its own reproduction. Like, it doesn't really care. Like, your lung cell will not reproduce out of control because it's going to be bad for the whole body. That lung cancer cell will reproduce wherever it wants, whenever it wants. It will move wherever it wants. So it's basically this, it's like the difference between a team sport and an individual player, right? Mm-hmm. So you have a team sport like basketball and you're trying to win. So each person has a role to play, right? Whereas a cancer is more like that player who's just hawking up shots, trying to pad his own stats, right? It may not be good it might be good for the team. It might be bad for the team. He just don't care, right? He's just throwing up shots, going wherever it wants, doing with no defense and all this sort of stuff, right? And that's the same with the cancer. It's sort of transformed into this team player, into this sort of individualist that's only concerned about itself. And that evolution comes about because as a response to chronic damage. So when you look at what causes cancer, they're all different forms of chronic low-grade damage. damage. So whether it's lung smoke or asbestos or viruses, or even things like ulcerative colitis, which is a autoimmune disease, for example. But more interestingly, even chronic medications that treat cancer can cause cancer, right? So radiation not only treats cancer, but it causes cancer too, because that's from paradigm one, where you're damaging cells. So by damaging the cell, if you expose it long enough, you can actually cause cancer. So radiation therapy, for example, sort of doubles or triples your risk of secondary cancers, which is cancers that come about because of the treatment. And same with the chemotherapy. There are various types of poisons. So they not only kill the cancer, but they can also cause a cancer. So that's the sort of understanding that we've sort of moved towards that is so interesting, because now, again, we can develop new treatments. Because now, again, we're not trying to develop things that kill, and we're not trying to develop things that fix the genetic mutation. What we're trying to do is develop ways to combat this new sort of evolution to a sort of invasive species. And our body has ways to deal with invasive species. So we have an immune system, and the immune system is now sort of front and center, because now we're like, okay, now we can actually bolster our immune system to target these cancer cells, because that's what's going to root out these sort of little sleeper cells of cancerous cells and stuff. So you have immunotherapy, which is the big sort of hope for the future, as well as prevention, of course, because once you understand what causes cancer, then you can try to prevent what causes it.
That's a good point to bring up, the chronic versus acute stressors. And you mentioned this chronic low-grade things like that keep affecting your body is what's at the root of this. And so maybe you could explain a little more about chronic versus acute and why one can be good and one can be bad.
Yeah, so the point is that if cancer is this evolutionary disease, evolution, if you think about Darwinian evolution, needs time. So you need a chronic stress, that is some sort of selection pressure, and then you also need time for everything to adapt. So if you compare sort of an acute stress, so radiation, we know radiation causes cancer, but if you have a single event, a very high intense radioactive event, such as Hiroshima, everybody worried that that would cause a lot of cancer. But the problem is that it doesn't cause it because there's no chronic selection pressure towards this sort of new phenotype. So when they actually measured cancer after the survivors of the Hiroshima bomb, it was actually way, 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 way lower than anybody had expected, which was great news, of course. Mm-hmm. But it just goes to show you that what causes cancer is not that single acute stress. Same thing with hepatitis B. So there are different hepatitis viruses. Hepatitis A causes massive fulminant liver failure. So a single event of a massive sort, it can destroy your liver, but it doesn't cause cancer. Whereas hepatitis B doesn't cause that catastrophic liver failure, but it causes chronic liver damage, and that's what acts as a kind of chronic stress on the system. So, and you can see that for everything. So asbestos, for example, you have to have chronic exposure. Lungs, tobacco smoke, you have to have chronic exposure. But you can expose your body to chronic other things like your stomach acid. So your stomach acid, when it refluxes into your esophagus to give you heartburn, well, that stomach acid, which is 100% natural, it's just in a spot where it's not supposed to be, but that low-grade chronic damage actually predisposes you to esophageal cancer, which can be actually highly lethal. And that's why diet winds up being so important, because it is a chronic stress, because we're eating it all the time when we have to, but if we eat different things, it's going to put us at different risk, but it's a chronic problem, not an acute problem.
That's super important. I want to get into diet later, but that's all I talk about on this podcast and with all my guests, and it's 100% correct. But I just thinking about the Hiroshima thing is if you lived close to the site and you got chronic exposure, then you would have cancer. Then that same thing happened with people who live near radiation sites, but it's not because it happened once.
Yeah, so that's why people worry about living near radioactive places or power lines or whatever, because it's chronic stress. The thing about Hiroshima is that because it was such a big single event, you had a high exposure and people died from radiation poisoning and so on. But it wasn't this kind of chronic, like there was radiation going on, but very quickly the radiation fell. people, of course, moved away from the site where all the radiation was. So they weren't exposing themselves to that chronic radiation as opposed to living sort of right next door to power lines or a radioactive site. That's where you're going to have the problems because it's that chronicity that allows that sort of evolution. You can't have it with a single event.
Well, that's like how our immune system works. I've talked about this with many people before, chronic versus acute. But if you go one level down of why it is like that, it's because your body can form a response to an acute stress. But if it's every day, then your body doesn't work the same way.
Yeah, it's just the difference. I mean, it's a different thing. So in medicine, we typically worry more about the acute event, and it's easier to study. A lot of our sort of, when you do studies, it's almost always geared towards acute events because it's easier to study. So you do these randomized control trials and you have a single thing intervention. But the problem is when you get chronic, if something develops over 20 years, it's way too expensive and the dropout rate is way too high. So that's the problem with that. And then it's a real issue because then people say, well, you have no evidence and stuff. And it's like, well, it's not that there's evidence against, there's just no evidence one way or the other. But yeah, it's the chronic events that are becoming more and more of an issue in sort of 2020 compared to the acute events, sort of COVID notwithstanding.
And then also with the hallmarks of cancer, that was really interesting how you talked about there's the same 4 hallmarks of single cell organisms. So you're talking about this atavism, this like going back, this evolutionary stuff. If you could try to recap that in a sort of high level way for the audience.
Yeah, so this was the sort of breakthrough in the 2000s. So everybody, as I said, looked at cancer separately. So lung cancer separate from breast cancer, for example. And in 2000, a couple of researchers decided, hey, what we're going to do is we're going to look at what makes cancers the same rather than what makes them different. So what is the same about these cancers and what is it about it that we can make this cancer? So there's actually 8 hallmarks, but I sort of condensed them into 4 sort of traits. The traits basically are they grow. So normal cells, so if you think about your body, if you think about your liver, say, it doesn't just keep getting bigger and bigger throughout your life until it's the size of a boulder, right? So it doesn't grow. It stays the same, which means that the number of cells that are sort of being born is equally matched by the number of cells that are dying. The second thing is that it's immortal. So cancer continues to grow. So if you take a breast cancer cell and just give it enough nutrients and all that, it will just keep growing until it is the size of a boulder, if you could supply all the things. And the second thing is that it's immortal. So cancer is immortal. It never dies. So if you think about your liver cell, for example, if you take that liver cell and plop it into the lab and just grow it and let it divide, it will only divide a certain number of times before it stops and will not go any further. And this is called the Hayflick limit. It's been known for quite a number of years. So cells are mortal. So you can't take your own cells. They have a natural limit to them. Whereas cancer cells have no limit. You can take a cancer cell, and we do that right now, actually. We take these cancer cells and we just grow them and we grow them and we grow them. And when we run out, we just grow some more, grow some more, grow some more. And they will divide indefinitely. And that's very similar to a unicellular organism. The third thing is that they move around. So if you think about your liver cells don't jump around. They don't go anywhere except where your liver is. And there's a reason for that. We stick things to where they're supposed to be because the liver has to be in a certain position to work with the rest of the cells. So just like if you have a team of soccer players, well, the goalie's where it's supposed to be, the defense is where it's supposed to be. There's positions. You have to stay in your position, right? You don't want your goalie running up, trying to score because then your net is going to be open. So there's certain positions and you need to stick there as opposed to cancer cells, which just basically go anywhere they want, right? And they metastasize. And then the fourth sort of trait is they have this unusual sort of metabolism in that they use glucose in a process called glycolysis as opposed to oxidative phosphorylation. So oxidative phosphorylation is where you take the glucose and you burn it and you get like 36 ATP. Glycolysis is where you get lactic acid and only like 2 ATP, so much less efficient way to grow, which is very interesting. And this is called the Warburg effect. And they say, well, why are cancer cells doing that? But that doesn't make any sense because if you think about growth, if it's growing like crazy, it should need energy. So therefore, why is it not using the more efficient way to get energy? And that's, the four sort of traits that cancer all sort of shares. And when you look at it, it's exactly the same thing that distinguishes unicellular organisms or single-celled organisms from cells in a multi-celled organisms. So if you think about a bacteria or a yeast, it grows, it's immortal, it moves around, and it uses glycolysis. It's exactly the same things because that's what differentiates. Those four things differentiate single-celled organisms and multi-celled organisms. And that's not a coincidence, right? They act exactly the same. So the stunning sort of revelation was that cancer cells act like single-celled organisms. So why? That's the question, why, right? And that's what opens that sort of realization is like, what's going on? So that's sort of how this paradigm comes about, is that we say that, okay, well, if you think about that liver cell, it initially evolved from a single-celled organism. So if you have a single-celled organism, the genes, and you want to make it into sort of a team player, right? Well, you need to put genes on top to control it. But that programming, the growth, the movement, glycolysis, and immortality, that programming, that cancer sort of subroutine is buried inside that normal cell. But what you've done is you put all these controls on top of it to make it act like in the way that you want. So essentially you're taking that sort of individual player, you're adding rules to make him a team player. And that's great. It works fine. The problem is when you subject that cell to stress, it now starts to face a threat to its existence. And in order to survive, it may choose to lose some of that extra programming put on top and allow that sort of cancer subroutine to go. And I make the analogy, it's like a survivalist in the woods, right? If you live by yourself, you have to be self-sufficient. You want to grow, you want to move around, you want to live in a sort of New York City sort of environment where you live with a lot of people. There's a lot of rules that go on top of that. But the benefit of those rules is that allows specialization into, scientists and lawyers and whatever, right? And then you will be much more effective. Like we can go to space, whereas a bacteria wouldn't develop that ability. But it's that specialization. But if you take that sort of person who lives in New York, throw him in the woods, put him under stress and throw him in the woods, it's still the same person. But now he's got to change. He's got to learn all those other skills, right? So he's sort of moving towards a survivalist. And that's the same thing that happens with the cells. It moves and it loses those controls on top of its original programming. And that's why the cancer is sort of evolving backwards. And this sort of paradigm explains so much about cancer behavior. Because if you think about it, the mutations that we see in cancer are not random. And now what we're seeing is the evidence that it's not random. That is, if you take all the mutations of cancer, and remember, there's like 6 million of them, and you don't say what do these mutations do? But what you do is you divide the mutations by their evolutionary age. That is, some genes are very recent. And you divide them by their evolution age and say, where does cancer really have its biggest impact? What you see is a sharp spike right between unicellularity and multicellularity. That is, when our cells evolved from the way back, from single-cell to multi-celled organisms, we had all these extra controls put on top of us. That's where all the mutations are happening. Cancer is actually removing all of these things. As you remove them, then you allow the original to shine through. And that answers a few questions. One, why do cancers all look the same? This is a very interesting question if you ever think about it. So if you take a breast cancer, so remember, a breast cancer or a lung cancer, so you take a lung cancer, it looks the exact same looking lung cancer under a microscope. So you take a Japanese man, in 2020 compared to an American woman in 1920. So opposite sex, opposite sides of the world, a century apart. Those two cancers have evolved completely independently from those person's lungs yet look exactly the same, right? So if it was a forward evolution, how on earth do you get that? Because as you evolve forward, it can go in any different way. You can evolve anything. Why are these cells that go from a normal cell to a lung cancer cell, why are they evolving the ability to move, to grow, to become immortal? It's the same strange portfolio of powers. Why didn't the cancer evolve the ability to shoot laser beams out of its eye, right? Like you think that because it's not part of the original programming. So it's not that you're gaining new abilities. Cancer is not gaining the new ability to metastasize. It always had that ability. It was suppressed because it's not good for the body. But now cancer is sort of uncovering it. Same with unlimited growth. Like, you know how cancers just keep growing, right? That ability was always there. It's just that you took the control off of it, right? And that's what's so interesting. And that's what this theory sort of explains to a much more satisfactory degree than this sort of random genetic mutation idea, which is crazy because if it was a random genetic mutation, two people's lung cancer should look vastly different, right? Very, very different from each other.
It's impossible to be the same.
It's like 100 different, say you had 100 password that had 100 characters. And it's like, you come up with the same two passwords like you and me. That would be impossible, right? It would only be possible if it came preloaded with that same 100 character password. And I just said, oh, here's my password. And you said, oh, here's my password. And they're the same because it came preloaded. So this sort of atavism, this sort of backwards evolution, it just fits the experimental facts to a much stronger degree than the somatic mutation theory, which was this sort of bunch of random genetic mutations that all happen to do the same thing. That's almost implausible. It just doesn't make any sense.
That's really interesting. I'm thinking about dogs and wolves. I don't know if you mentioned your book, but I don't know if you made this parallel where all the DNA information to make all the dogs we have was there in that wolf. I don't think we developed new things that created these new types of dogs. It's just we expressed genes through the natural selection that the humans directed into all of this information that was already there. Does that work?
Yeah, exactly. So if you say, yeah, that's what I said in the book. If you think about a wolf, an ancestral wolf eventually becomes a dog. Now that's a forward mutation. We've bred dogs for this and that and this and that. So you have Chihuahuas and you have like greyhounds and you have, all different kinds of dogs. The variation is basically infinite. And you get new stuff like Labradoodles and, those designer dogs that are so popular now, right? Like nobody had a Labradoodle before, right? So the point is that when you're evolving forward from a wolf to a dog, the variation is infinite. If you have a lung cell which turns into a lung cancer cell, the fact that they all evolve along the same pathway means that it wasn't this sort of forward evolution. It couldn't be. It's impossible for that to happen because otherwise you'd have this incredible variation in what it is that we're doing. And what's interesting too is that if you look at cells, the way they're described pathologically is actually exactly what we're talking about. That is, they've always been described as primitive cells, right? They look primitive. They're dedifferentiated. So it's not that we're not saying that these cells, these cancer cells, are more advanced looking. They're actually the opposite. They're sort of going backwards in evolutionary time. They're actually looking more primitive. What we saw with our microscopes is actually describing exactly what is happening from an evolutionary standpoint. We just didn't acknowledge it at the time. But that's why this sort of new theories are so interesting because it really tells us about what is sort of going on at a higher level.
Are these being accepted? So I know a lot of these things in science, when people come up with these new paradigms, I always like the Thomas Kuhn, the false, trivial, obvious, where it's the nature of scientific revolutions. And first it's false, then it's trivial. It's like, oh, it doesn't matter. And then it's obvious. We knew it all along, right? And that's how things tend to go in science. So I don't know what stage we're at with this view, but it seems like this view makes a lot more sense.
It makes a lot more sense. And I think that I've listened to a few people talk, and certainly there's very so a couple of other oncologists. I mean, I didn't make up these theories, right? These are all there in the literature. When you listen to some of the podcasts from some of these cancer specialists, clearly they understand that it is an evolutionary disease now. It's almost a throwaway. They say it's an evolutionary disease and then they explain it. What are we talking about here? Mm-hmm. And that's sort of what this book is about. So these ideas are not really my own ideas. I think they're on that leading edge of where science is going, but it's clear that because it's relatively new, most people have this other idea that cancer is this random genetic mutation. And we've actually moved past that. But I think we're at the beginning of this sort of acceptance. So most of the people who really think about this have already moved past that sort of, hey, this is a bunch of random genetic mutations that happens spontaneously. It's just too improbable. That just doesn't work. It's clearly not random. It's something that's deeply embedded in the way that multicellular life is done. Because again, if you think about cancer, it's an extraordinarily common disease. That is, if you look at prostate cancer, if you live to 90, I think 50% of men have prostate cancer. So it's not rare. It's just very, very common. So again, if it was so common, then how do you explain why it's so common? Why is every cell in the body potential cancer, right? You have cancers of the eyes, you have cancers of the heart, you have cancers of the placenta. Every single thing that is in our body is a potential cancer. And it's not just us. Every single multi-celled animal practically can get cancer. Maybe there's one exception, the naked mole rat. That's about it, right? But virtually every other animal can get cancer. So again, why is that? And I always think this whole genetic theory, which is that you have random genetic mutations. And it's okay, when you start randomly doing stuff, it's almost always detrimental. Mm-hmm. Right? So if you have a random mutation, it's almost always worse than the original, right? It's like taking a very highly tuned watch and whacking it with your hammer, and randomly it works better. It's that ain't going to happen, right? Mm-hmm. So it's why would we think that a random mutation would make this cancer, give all this cancer cell these superpowers, right? Oh, it becomes immortal and it can move around and it can grow as much as it wants. Why would it develop this superpower? Or, hey, it develops the ability to grow new blood vessels because I randomly whacked it. It's what are you talking about, right? If you keep randomly whacking your watch, it just breaks. It doesn't work better, right? And this was the whole idea behind this sort of genetic, is that it's all random and it all just sort of happens by chance. And it's the stuff is just too similar to be all chance. And that's why these theories, I think they're on the beginnings of being accepted. I mean, I think that a lot of people have already accepted them. The evidence is coming out now, but it's important because most people don't know about them. And that's what I want people to know about.
Well, yeah, I've never heard of it. I'm going to read your book again. I've never read a book twice, but I thought it was so interesting. And I was just thinking about Otto Warburg. You mentioned him, and I had some people on, talk about cancer, and Dr. Thomas Seyfried and some other people listening will be familiar with the Warburg, and there's oxphos versus glycolysis. And maybe you could just go a little bit more into that, because that's super interesting, right? It's why do cancer cells want to use the less efficient version?
Yeah, and I think there's a lot of theories on that. So the Warburg effect is that, so there's two ways that cells can generate energy. If you go back again in evolutionary time, the first way that was developed was glycolysis. So you take glucose, which is your energy source, and you get 2 ATP, 2 lactic acid. And most bacteria do that. That's why you ferment stuff, right? You get lactic acid if you make sauerkraut or something, or stuff spoils, you get lactic acid. So that's a very primitive way of generating energy. Then this next thing to develop was photosynthesis, which isn't really relevant here. And then you develop oxidative phosphorylation, which happens in the mitochondria. And again, you take that same glucose, but you sort of burn it clean. That is, you take all the carbons of the glucose and you generate energy. So you get 36 ATP and no lactic acid. For one glucose, you're going to generate 36 versus sort of 2. So it's a way more efficient way to generate energy. So our cells almost always use oxphos when we have oxygen, because it requires oxygen. So whenever there's oxygen, we almost always use oxphos because it's so much more efficient. So the question is, why does cancer, in the 1900s, what they observed, so Otto Warburg was saying, well, let's see what cancer does, right? Cancer is growing and needs a lot of energy, so he expected it to use oxphos, but it didn't. It used glycolysis, which is that much more primitive form of energy generation. And he thought it was so strange, like it's so bizarre. In the book I say, it's like you build a sports car, right? And you put it low to the ground, and you get a nice sleek, and then you take out the sort of 600 horsepower engine and you put in a 9 horsepower lawnmower engine. And you go, whoa, what the hell? Why are you doing that, right? That's crazy. Same thing with the cancer. You have this cell that's busy growing all over the place, needs a lot of energy. Why are you using such an inefficient way of generating that energy? It doesn't make any sense. And so Otto Warburg thought it was so bizarre that he thought that has to be the sort of original sort of sin, if you would. That's the defining thing. Damage to the mitochondria makes it not, so any chronic damage mitochondria as well. So again, that's sort of on the right track. But then he said it's that damage to the mitochondria that blocks you from having OSPHOX, that leads you down glycolysis, that leads you towards cancer. That's the sort of seminal event of cancer. And this was in 1957, a very famous paper in Science. And the problem was that some people still subscribe to that, but most oncologists have sort of said, well, it's hard to find experimental evidence to really support that. That is, not all cancers, like you can take a cancer cell and you can make it generate energy through oxphos, like it happens. The other thing is cancer cells, you can show that they metabolize proteins too. So you can do PET scans, show how much glucose a cancer cell is taking up. And that's why it lights up on the PET scan. But it can do other things. You can use certain amino acids, for example, and they'll do the same thing. So it doesn't need glucose in that way. It likes glucose, but it doesn't need it. And some cancers use fats. And then you can find cancers that have perfectly normal mitochondria. You can take normal cells, damage their mitochondria, and they won't turn into cancer cells. So it was hard to really pin that down as a whole hypothesis. So the question is, again, why? And again, one is that it's a more primitive form. But the other thing that has gained a bit of attention lately is two things. One, and this is what most conventional oncologists believe, and I think that there's a good chance, is that, so if you take a cell to generate energy, you take one glucose molecule will generate 36 ATP versus 2. That's only an advantage if glucose is limited. Right? If glucose is unlimited, that's not an advantage. So you can actually generate more glucose faster, like you can generate more ATP at a faster rate using glycolysis if you use sort of 10 times the amount of glucose. And that's the strategy that the cancer uses. So in a sort of sea of plenty, that increased efficiency makes no difference. That's sort of like if you have a car uses gas, and you have an energy efficient car, which uses little gas, and you have a big gas guzzler in the back of your house. You have you live in Saudi Arabia and gas is like super
unlimited,
cheap. And that everybody drives a gas guzzler.
Yeah, why not? Why not? Yeah.
Why not? Yeah, exactly. Because you can go faster. You can use more. Same thing with the cancer. If there's tons and tons of glucose there, then oxphos is not an advantage. And the other thing is that because you're generating these carbons, so remember, when you use oxphos, you're burning all those carbons. So we're carbon-based life forms. So all of our molecules, all organic molecules are based on carbon. If you take that carbon in the glucose and just burn it all, there's nothing left. You have no building blocks. As opposed to if you use glycolysis, you get 2 ATP, but you get 2 lactic acids, which you can actually use. It has a carbon skeleton, and you can use it to form other things. So what I'm saying is that, so if you think about building a house, for example, you need 2 things. You need energy, and the brick maker, the house construction workers need energy. But you also need building materials. So if you have 10 construction workers with energy, but no bricks, you can't build a brick house. You need both. So same thing if you're trying to build cells. You not only need energy, you need those building blocks. And the glycolysis actually provides both versus oxphos, which provides only energy but no building blocks. So perhaps that's an advantage of glycolysis. And the other thing that's very interesting is that maybe the lactic acid is actually not bad. Like, we consider lactic acid a waste product, but maybe for that cancer, it is precisely the reason why, like, most cancers use glycolysis, right? So if you say, why are almost all cancers using glycolysis to generate lactic acid, is like, maybe the lactic acid is a good thing for them. And that's a very interesting hypothesis that is only sort of recently been considered, which is that that lactic acid actually does a lot of good things for a growing cancer cell. That is, whenever cells are in competition with each other, you can either get better yourself or you can damage everybody around you. And that's what the lactic acid does. It creates this sort of hypoxic, acidic environment where other stuff can't get at it. Then what happens is that you attract the immune system, which sounds like a good thing for us, not the cancer, but it turns out it winds up, these growth factors get secreted into it from the immune system, and that may actually help the growth. So you have these tumor-associated macrophages, TAMs, for example, which are attracted by this hypoxic, acidic environment, and maybe that actually helps the cancer grow. So maybe the lactic acid is the reason that cancer is choosing to use this specific form of energy generation. And again, it's a completely fascinating hypothesis. I don't know if it's 100% proven, but again, makes a lot of sense. As opposed to saying that, the thing is that, like, if you look at the Warburg effect, glycolysis, which is aerobic glycolysis, it's like sort of like 80% of cancers use it, right? And it's like, is it just some random mistake? Or is it likely that this is something that cancer chose to do? And it's like, well, if it works, that is, cancer works, then it's more likely that this is something it chose to do. It's not a random occurrence that these cancer cells are all abandoning oxphos and going to glycolysis. So very interesting hypothesis. So maybe for several reasons. One is that there's lots of glucose around. It's not a limiting factor. Two, it generates carbon skeletons in addition to energy. So it's actually a more balanced way to grow, just like bricks plus construction workers versus construction workers alone, right? Mm-hmm. And three, maybe the lactic acid actually helps the cancer grow and metastasize because it sort of, okay, so you have all this acid that's sitting around the tumor. And remember, the cancer is spending energy to generate more acid, right, all the time. And this acid actually makes it easier for it to spread. It basically weakens all the extracellular membranes, basement membranes, allows it to penetrate other things like blood vessels and stuff, right? That acidic environment is damaging those other cells around it, which is good because if it's bad for the other guy, it's good for the cancer, right? So really interesting hypothesis. Once you start to take this sort of evolutionary view of cancer as an invasive species, then you can say, okay, well, can we understand why it's doing that? And these are interesting hypotheses as to why we can exploit this, perhaps, in a way.
Well, we should get that last, is how to exploit it. Now that we know this, how can we help? But before that, you're talking about growth signals and thinking about insulin and mTOR and AMPK. I wanted to make sure we hit on that too. Just how does this stuff start? How does this happen? How do you get these?
Yeah, so sort of in the last 10, 12 years, there's been an increasing recognition that our body uses nutrient sensors. When you think about a single-celled organism, it will grow as long as there's food. So you have a yeast on a slice of bread that you've left out. It will grow as long as there's food, right? If there's no food, it'll just stop growing. That's it. It doesn't need a nutrient sensor. But as we develop these sort of into multi-celled organisms like humans, like our kidney on the inside has no idea if we're eating or not. And neither does, your liver. It's like your liver's way over here. You're eating over here. How is it going to know if you're eating? And the reason it knows is because of these nutrient sensors. So we have actually 3 different nutrient sensors. So insulin was sort of the first one people knew about, but it's actually not the most ancient. So when you eat, insulin goes up. And that's one of the ways that it signals to the rest of the body that, hey, food is available. That's what a nutrient sensor is. mTOR turned out to also be a nutrient sensor. So this was discovered because of the rapamycin, the drug rapamycin, which blocked mTOR. When scientists were trying to discover how this drug worked, it's like, hey, there's this whole new pathway that we didn't know about called mTOR. And mTOR goes up when you eat protein. So you eat protein, mTOR goes up. So again, signaling the body that, hey, food is available. And that's a really important signal because it turns out that and AMPK is something different. It's the ratio of AMP to ATP. But it just signals how much energy is available, total energy in the cell. It's actually the opposite. So the lower the AMP, the higher the sort of cell energy. But it's essentially like a reverse sort of fuel gauge of the cell. So it also is a nutrient sensor, but it's not specific for glucose or protein. It's the total energy of the body. So these are the ways that the body senses the availability of nutrients. Turns out that these are also very important growth signaling mechanisms. And the reason why is because your body only wants to grow more cells if food is available, right? Makes sense. If there's no food, you don't want all these cells just growing and growing and growing because you need to feed these cells and there's no food available. So that's why our body evolved these nutrient sensors, but it used the exact same molecule as a growth sort of factor. So insulin is not only you eat, insulin goes up, it's a nutrient sensor. So insulin is not only a nutrient sensor, but it's also a very important growth factor. And growth factor, of course, if you have a bunch of growth factors, it's going to favor the development of cancer, which is a disease of excessive growth. Insulin, for example, leads to insulin-like growth factor, which plays a role in the development of certain cancers. You have genetic variants with almost zero insulin-like growth factor, and they're basically immune to cancer. So the reason that's important, again, is because these are the same molecules. In fact, if you go back to primitive organisms, insulin is not a nutrient sensor. Insulin is a growth factor. So it's the same thing. So this makes it important because if you have too much insulin, you have too much growth signaling. You're giving your body the signal, grow, 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 grow. And so those cancer cells are going to grow. So therefore, we're in this situation where we have diseases of hyperinsulinemia, obesity, and type 2 diabetes, for example. And again, we've just recognized within the last sort of 20 years, those conditions are actually huge risk factors for cancer. So these obesity-related cancers, there's like 13 of them that are designated by the World Health Organization. And we didn't know that sort of until about 2003. We didn't even know that obesity was this risk factor. We didn't even know that type 2 diabetes was this risk factor. But it probably all comes down to insulin and mTOR and AMPK. So now you get these ideas, for example, like metformin, which impacts AMPK. It's an AMPK activator. If it activates, it goes up, it signals that there's less energy available, lowering growth. So now you get all these people who are like, well, maybe we should use metformin. And there's some evidence that type 2 diabetics who use metformin compared to other types of drugs have less breast cancer, for example. So very interesting stuff that sort of reinforces the importance of these growth factors. And of course, mTOR, if you block mTOR, that's used in certain types of cancer. So you block mTOR for kidney cancer, for example. So again, showing the importance of these nutrient sensors for cancer.
That's great because metformin, well, that's too late. It's using these medicines to attack the symptoms, but getting at the root cause of the problem, which is how we can end this discussion and how we started, is that hyperinsulinemia is kind of at the root of all of this, is how do you live and eat so that you don't have to retroactively use a drug like metformin to get down your insulin and your growth factors?
Yeah, and that's the sort of trying to avoid these diseases of too much insulin. So again, low carbohydrate diets, avoiding a lot of processed foods are going to reduce your insulin level because some foods stimulate insulin a lot and some foods don't. So therefore, cutting out the sort of refined grains and stuff is going to be highly beneficial in those diseases. The other thing is intermittent fasting, of course. So fasting is going to reduce not only insulin, but mTOR, and it'll raise AMPK as well. So it's going to signal to the body that, hey, no nutrients are available, stop growing. So your body sort of either is in growth mode or it's in sort of maintenance mode. You want to shift it towards maintenance mode because that's going to be less conducive to the development of cancer. So these sort of ideas wind up coming back to sort of don't eat all the time. Make sure you have sort of this daily fasting period where you're not eating. Try to eat real foods, because if you look at the insulin effect of real foods compared to sort of highly processed foods, it stimulates much less insulin. Those are a couple of the things that you really want to focus on, but really getting back to, a normal weight, reversing type 2 diabetes if you can. We know that those are big risk factors. If you can get rid of those, you're not going to have as much chance of cancer.
Well, yeah, this is what I always talk about. It's a simple unifying theory of all diets and all people that don't have a lot of disease and cancers and all these things. You don't really eat all the time and you don't have these high insulin spikes. You're not eating processed foods. Okay, maybe we should go back for a second to our ancestors or people like the Inuit, or there's certain people that don't seem to get cancers. And why? So they have these cells. If cancers, you're kind of saying it's already there, but it's whether it's expressed or not. So certain people don't express things if you don't live a modern diet and lifestyle.
Yeah, and this was the observation from Dennis Burkitt in the 70s. This is what he observed. So this was an Irish surgeon. He goes to Africa. He actually discovers one of the causes of cancer called Burkitt's lymphoma, which is a viral disease, actually. But what he observed was that the Africans who ate a traditional diet and lived a traditional lifestyle didn't get the types of cancer that the whites were getting. And if you look at the Africans who started to go into the cities and eat and live like the Western civilizations, they started to get cancer. So again, the idea is that you have the seed of cancer exists in all of our cells, but the soil that you provide it, like the way it grows, is what determines whether that seed blooms or not. So eating that traditional diet in Africa, for example, it was inhospitable soil for this seed of cancer. They didn't get colon cancer. Then they eat refined grains and sugar the way that the whites were in Africa, and all of a sudden, they got that. Same with the Inuit, which used to be called Eskimos, so in the far north. So eating their traditional diet, they had so little cancer. And these are the breast cancer, colon cancers. They got the viral cancers. But they had so little cancer that one of the universities in Canada used to send an expedition to the North Pole practically every year to see why these Eskimos, that's what they called them at the time, were immune to cancer. And it's turns out that they weren't immune, because as soon as they started modernizing, eating sugar and eating flour and white bread, they got the same cancers. So that's what Dennis Burkitt called the diseases of civilization. And it's not the person, it's not the genetics, because you take that African, for example, then you make him eat sugar and white bread and he gets colon cancer, right? So it's not the genetics that was important. The overwhelmingly important factor was, in fact, the diet. And again, it's probably related to a lot of things, but one of the big ones is probably the insulin levels. So I remember there's an old study on the Katavans from years ago where this Swedish guy, he went down to the Katavans, and that's an island in the South Pacific where they're eating a lot of traditional foods, fish and coconut sort of thing. And he measured their insulin levels, and their insulin levels were sort of at the 5th percentile of a normal Swedish population. That is, them eating that sort of very, very traditional diet, their average insulin level was sort of lower than 95% of the Swedish population. And remember, Sweden, there's not a lot of obesity. This is back in the 70s and stuff. There's just zero obesity at the time, and Swedes are better than us. They've always been better than us, right?
For sure.
Athletic and all this sort of stuff. It's a healthy Swedish population. And these Katavans had insulin levels way lower. So remember, insulin is not just a nutrient sensor. It's also a growth factor. So if you're having super, super, super low insulin levels based on these traditional diets, well, you're going to create an inhospitable soil for this cancer seed. And that might be one of the reasons why these traditional societies just never got these cancers, which led to Dennis Burkitt calling them cancer, a disease of civilization, which again completely flies in the face of this idea that it's a genetic disease. It's not.
I hate that it's mainstream ideas that obesity is just genetic and we can't fat. Well, that's a whole nother thing. They just keep blaming it on the genetics when we're talking about it being the host. It all comes together actually when we're talking about cancer or Alzheimer's or obesity or COVID. You have to give yourself infertile ground for each of these to grow. If you are very healthy, have a very strong immune system, and COVID comes your way, your body can fight it off and you probably won't be affected by it. It's the one thing that we can control. Yeah. And if you live the modern lifestyle and eat fast food and eat refined foods, then you're going to be susceptible to all these diseases.
The whole thing is that, COVID, we're learning more and more about COVID, but of course, obesity is a big risk factor. But obviously, there's not a lot of science yet because it's a new virus. But it's striking how much of what kills Americans is related to that, right? So cardiovascular disease, number one, cancer, number two, killers of Americans. But, you've got all the diabetes and, the obesity, which contributes to all this other stuff, and the strokes and the Alzheimer's. I think it was 7 of the top 10 causes of death in the United States are all related to this problem of hyperinsulinemia. And the thing is that is something completely in our control if people would just pay attention to it, right? Because it's all related to diet and lifestyle. So if you say increase the amount of fasting that you do, well, that's going to lower insulin because fasting lowers insulin. There's nothing more complicated to it than that. And if you look at sort of 1960s, 1970s, well, people did used to fast. They didn't eat all the time. Whereas now we think we should eat all the time. And it's okay, that's a crazy idea. And why we would ever accept this idea to allow these diseases of hyperinsulinemia. And I think that's very powerful because people talk about insulin resistance, but that's a terrible way to phrase it, because when you say you have insulin resistance, it doesn't tell you what you're supposed to do. Because there are vegans, for example, who say, well, if you eat fat or if you eat eggs, right? If you eat fat, you will get insulin resistance. It's I don't think so. But if you frame the problem as hyperinsulinemia, it's a disease of hyperinsulinemia, now you know the solution. My insulin is too high. How am I going to lower my insulin? And then you say, well, that's simple. You lower the refined carbohydrates you take, or you increase the fasting that you do. Both are easily recognizable as ways to lower your insulin. And if your insulin is too high, then you lower it. As opposed to saying it's a disease of insulin resistance. It's okay, so what do I do now? Do I eat less eggs, less fat, right? There will be people who argue that that is what you're supposed to do, whereas it makes no sense to me to do it. So that's why I always refer to these diseases as diseases of hyperinsulinemia, just so that it's very clear what the next step is. Lower it. That's way easier to think about.
It is. It's just hard to get people to do it. I think in my mind, we have it pretty well figured out that you need to not eat all the time. Maybe if you eat too much, you can exercise. You don't have to exercise per se, and you just eat unrefined foods. But in a modern civilization, no one wants to do all those things. And therefore, we're left with all these problems.
Yeah.
So I know you have to go in a second, but yeah, what's your kind of wrap up here, and what can we do, and maybe specifically to cancer, and what are you excited about for the future?
I'm excited, one, in that we're getting new treatments, but two, the more we can understand that some of these are diseases, and cancer, we'll say, is not all just in hyperinsulinemia. It plays a role, but lung cancer is not about hyperinsulinemia. It's all about smoking for lung cancer, right? So you have to figure out what specifically is the cause and then get to that root cause, or hepatitis B or whatever. But what excites me is that if you can understand these things, then you can do something about it, and you don't need a doctor. You don't need a dietitian to do these things. You can say, look, I'm really scared about getting cancer, breast cancer, for example, or colorectal cancer. Those are two of the obesity-related cancers. Well, then you can simply say, well, I need to lose weight. Well, I can increase my fasting. I can cut out the processed foods. I can cut out all the junk foods. I can cut out the sugar. Those are all within our own control. But it's, again, understanding that it's not a one-time thing. These are all chronic diseases. So if you make that commitment because you don't want to get cancer, well, you need to stick to it in the long term, not like I'm going to cut out sugar for 2 months and then binge on ice cream sort of thing. It doesn't work like that because these are chronic diseases. So, but the more you understand about these sort of diseases and what influences them, just like we did with smoking, right? We made everybody aware. And honestly, it took a lot,
there's campaigns and so much money involved. And
huge, right? To get people to stop smoking. And that's probably the most important thing we've ever done in the history of cancer therapeutics is get people to stop smoking. So it's going to be the same for obesity and sugar and insulin and stuff. But the more you know, the sooner you can start to think about these sort of things. And if people don't want to, just like stopping smoking, right? You do these things to reach the people who don't know any better. But for the people who want to do it, you don't need anybody's permission. You don't need anybody to tell you that you can or can't stop smoking or can and can't fast or can and can't, cut out sugar, that kind of thing, right? It's really important to give people the knowledge so that they can make their own decision, right? If they want to smoke, then you can smoke, but that's your own decision. You know the facts, you take your own risks. But for those people who don't want to smoke, well, they have the right to that knowledge so that they can quit if they want to, right? And if people have trouble, which they do, then we'll help them. We'll put groups together for stopping smoking. We'll, legislate that you can't smoke on an airplane. Which was honestly the dumbest thing we've ever done.
It's hilarious. There's more and more programs and support groups and social media and this and that to help people. And also, I think there's a hopeful message going back to the chronic versus acute. People are chronically eating sugar and chronically eating junk food. We're not saying you can never have anything ever again that's sweet. Because if it's an acute situation, your body can deal with it. If you have one piece of cake once a month, your body's like, okay, I'm going to deal with this. But if you have it every day, it's completely different.
For sure. I mean, that's the bottom line, right? A little bit is okay, but all of a sudden you eat cake every day, which is what a muffin is, basically. Now you're going to have a problem.
Well, there it is. I really recommend the book, Cancer Code. Where else can people find you?
So you can go to my website, which is thefastingmethod.com. You can also look me up on Twitter, which is at Dr. Jason Fung. And also on YouTube, you can check out my videos, which is under Jason Fung. Those are all great sources of information, and you can find me there.
Thanks so much. And I really enjoyed your book, and thanks for coming on.
All right. Thanks, Brian.
All right. Thanks for listening, everyone. Please share this with family and friends. Give it a review on the iTunes or the podcast app. Go to nosetotail.org for all the delicious meat, the new products, the hats, the body care, the seasonings that I didn't mention in the beginning, the biltong, and also sapien.org for everything else like the tribe and the diet and lifestyle program. If you're ready to make some significant changes in your life and get healthy. Until next time, take care.